goal of this session is just to cover as much content as quickly as possible. As I'm doing that, I have the chat open. I'm going to be reading your comments, seeing what you guys are saying, and responding to them live. So the goal is just to go through as much content as possible so you feel a little bit less cooked walking out of this tonight, and a little bit more ready for Tuesday morning. So the way any of my lives ever work, the more questions you ask, the better the live is for everyone. So keep putting your questions in the chat. I will respond to them as quickly as I can. And we're going to make it a great session. And I don't know how long it's going to be. Might be an hour, might be a little bit longer than that. It kind of depends. I will actually be live with Chegg tomorrow night too, over at my whiteboard. So find me on TikTok tomorrow night at 8:30 p.m. too. So the goal with that session is just to go through as many questions as possible. So I'll just be at the whiteboard. Hopefully by the end of the session, I will be covered in marker because we're just going to do as much AP Chem as we can. Shout out to AP Bio Penguins and everyone getting ready for Cinco de Bio tomorrow. I know that's a huge double if you were trying to do AP Bio and AP Chem. That is a lot. All right, let me see if I can get my slides to work since they would not upload. We'll try this. This should work. Okay. Let's see. Yeah, and everyone's asking, okay, what are the percentages for 3s and 4s and whatnot? And the thing is, on the AP exam, like, you wanna always you wanna aim high, right? Like, you wanna do the best you can, and you can't really go into it saying, "Oh, I'm gonna aim for a 60%." You're gonna do the best you can. You're gonna sit down, you're gonna show what you know. I will say that the exam has trended on the easier side the last couple of years, so let's hope that that's the case on Tuesday as well. But yeah, you're gonna aim high. All right, we're gonna go ahead and get started. So first of all, who am I? My name is Corinne. I run Chem with Corinne. Basically, I was a chem major. I went on to grad school because I loved chemistry so much. I always had teachers who believed in me. Went on to grad school. I was studying astrochemistry. What did I love about astrochemistry? Not a lot. I was spending more time enjoying being a TA, and I started coaching high school cross country and track when I was like, maybe I don't want to be a research scientist anymore. Maybe I want to go into teaching. So I switched gears. I actually worked in neurology for a little bit before I decided to go back to school. So did both of my graduate degrees at the University of Virginia. Go Hoos. And then I became a teacher, and I've been teaching ever since. So yeah, so that's a little bit about me, but this session is not about me. The session is about you and helping all of you tonight. So I apologize that the slides were not working, but what we're going to do is we're just going to run through it anyway, and we're going to make this work because that's kind of how you have to approach AP Chem, right? You recognize that there is so much about this class where all of a sudden you're like, oh, wait, I don't know how to do that, right? I have never seen this, but you will get there. You will figure it out. Okay, that's not going to work. Let me see. Here, let's see. We'll make this work. Okay, let's keep going. All right, we got people from all over. It looks like someone else is from Virginia. Awesome. All over the country. Okay, stop saying you're cooked. You're not cooked. I promise you are not cooked. It is going to be okay. You've made it through AP Chem at this point. You haven't dropped the class, right? You know what you're doing. You're doing okay. All right, so goal with this session, we're going to focus on the big ideas first. What are those big ideas that you see over and over again, the overarching ideas that come into lots of different units? And you know what those FRQs look like, right? Where all of a sudden you're hitting on 16 different topics in one FRQ. Then we're going to just actively engage with practice problems. I have a whole bunch of content built into this slide deck so that whatever your questions are, we can jump around and just hit on those topics that you're most concerned about. And then I'll just be answering questions from the chat for as long as I can keep up with them. If you also see this laptop, if you download the slide deck, it's just linked as a PDF. Any of those laptop icons just have direct links to short videos and other resources just to try to help you out as you continue studying for Tuesday's exam. All right, so let's get started. Big ideas. These are the big ideas I'm going to focus on. Effective nuclear charge, Coulomb's law, Coulombic attraction, Q versus K, TDF, thermodynamic favorability. I never knew that was the acronym for it, but TDF is so much easier to say, so that's how I will be referring to it. And then IMF, intermolecular forces, because as everyone knows, Unit 3 is worth up to 22%, and a big percentage of that could be intermolecular forces. All right, so let's get started with the first buzz phrase. And I used to joke that this is all you need to write on your FRQs for a 5. Not quite true, but let's actually talk about this concept because it sounds really intimidating and it's not. right? Effective nuclear charge. What am I talking about? So it just says that the larger the number of protons you have in the nucleus, the more those electrons are going to be pulled inward toward that. So effective nuclear charge literally describes the number of protons in that nucleus and the magnitude of that positive charge. So when we think about periodic trends, it's all going to be based on this idea that as we move across a period, right, I am adding protons to the nucleus. As I add protons to the nucleus, the magnitude of that positive charge increases. And what happens? The negatively charged electrons are more attracted towards the nucleus. So the Coulombic attraction increases, which we're going to talk about in a second, bringing that radius and shrinking the radius slightly. So basically, the reason you need to know this buzz phrase is that the greater the effective nuclear charge, the smaller the atomic radius, just because of that attraction between the positively charged protons and the negatively charged electrons. Yeah, and okay, so let's see, Coulomb's law. Yes, we're going to talk about Coulomb's law right next. And then will this video be posted? Yes, I will post this. And I will probably edit out all the extra info and I will add in chapters so you can just pop into whatever topic you need. I don't like to waste time, and I know you all don't have a lot of time. So I will try to organize that as well as I can for you. All right, next big thing that you really need to be really comfortable and confident with is Coulomb's law. So this is the actual law. The force is proportional to the magnitude of charge, Q1 versus Q2. Those are your two charged particles, and inversely related to the distance between those charges. What does that mean, right? In straightforward terms, the greater the magnitude of charge, right? So if I have an ion that has a +2 charge versus an ion with a +1 charge, the +2 is going to have a stronger attractive force to a negatively charged ion, versus also the greater the distance between charges, the smaller that Coulombic attraction or repulsion. So when we're thinking about Coulomb's law, understand that it's the electrostatic forces. Really fancy way to describe that attraction or repulsion between two charges. So if they have the same sign, right? There's going to be a repulsive force where they're pushing away from each other, versus the attractive force, we have oppositely charged particles coming towards each other. This all sounds really fancy, but again, it is not as bad as it sounds, right? When you put it all together, that's what's going to determine all of those periodic trends, which are all based on atomic radius. So if we think about as the effective nuclear charge increases as we're moving left to right across a period, what does that mean? Greater magnitude of positive charge, the negatively charged electrons move in towards that because of Coulombic attraction, and that's going to reduce the size of the atomic radius. And the atomic radius is going to kind of decide all of the other trends, but we'll talk about that in a second, I think. All right, so that's like the first two big ideas, right? With periodic trends all being based on this idea of effective nuclear charge and Coulomb's law. The other thing you need to be really comfortable with is discerning between Q versus K. And a lot of students are like, what is Q again? Q is the reaction quotient, and guess what? It is calculated exactly like K. The difference is the reaction quotient is just referring to any time other than equilibrium, versus the equilibrium constant, K. You've done a lot with equilibrium constants at this point. When we're looking at K, it's the concentration of products over the concentration of reactants raised to the power of the coefficients from the balanced equation. So when you're looking at Q versus K, the question is, why do I care? Why do I care about Q at all? Well, you're going to care about Q in thermochem, and it's going to come back in electrochem. So let's look at that. So when we're thinking about Q versus K, the Q, the reaction quotient, if we compare that to K, it's going to indicate the direction that we need to go to get to equilibrium. So if Q is greater than K, what does that mean? I have a higher concentration of products over reactants. What does that mean? The reverse reaction is going to be favored. Versus if Q is less than K, that means I have more of my reactants than my products, and the forward reaction is going to be favored. If Q and K are equal, we know that the system is at equilibrium. And then when it comes to K, why do we care about K? If K is large, so if we say if K is much greater than 1, the products are favored. So we're forming more product at equilibrium, versus if it is less than 1 or very small, the opposite is true. We are forming more of the reactants. And if K happens to be equal to 1, if we think about K again, K is equal to the concentration of products over reactants. If K equals 1, then the concentration of products is equal to the concentration of reactants. All right, Q versus K. Let me jump back into the chat. Yes, and K is always Products over reactants. That's a really good question. So when it comes to K, a lot of students get confused with KSP because they're like, wait, but KSP is only products. Why is KSP only products? Because equilibrium expressions do not include solids or liquids. So when you think about KSP, which is the solubility product constant, right? If you have a solid precipitate separating out into its ions, right? When we think about writing the KSP, the reactant isn't included in that. So it's going to look like it's only the concentration of products, but that's just because your reactant is a solid. Yeah. Okay, let's see. So any practice MCQs. Yeah, so MCQs are hard to find. So your teacher has access to those in AP Classroom. Those are not released. I know that Princeton Review has pretty good MCQs, but they're not perfect. And if you did not see Mr. Faribault's live last night, he did go through, I think he had 30 MCQs. So definitely check that out. He was actually my mentor teacher a long time ago, and I decided to go back into teaching. But I know he went through a bunch of MCQs. So if you're looking for more practice with that, definitely. And I have some practice problems built in. So we'll do a little bit of MCQs, a little bit of FRQs. Yeah. All right. So let's move forward. Other big idea you need to be really comfortable with: thermodynamic favorability. Blah. TDF, right? And a lot of students will ask at this point, like, can I use TDF on my FRQs? Yes, you actually can. So when it comes to abbreviations on the FRQs, you want to go ahead and write out thermodynamically favorable once, put it in parentheses, and then you can use TDF after that. You have to do that for each question, though. If you want to use abbreviations, recognize that your graders are going to be passing the test. They grade on a question by question basis. So if you define TDF in long question 1 for the FRQs, and then it comes up again in your short answer questions later on, you have to redefine it. So if you want to use abbreviations, you can, but just make sure you're defining it in every single question. Yeah. All right. So let's go back. So thermodynamic favorability. You just got to memorize these quantities. So you're looking for a negative enthalpy, positive entropy, so an increase in the dispersal or energy, and then negative Gibbs free energy. K greater than 1, you can really have any K, and then a cell potential, so E dot cell, that is positive. So definitely memorize those quantities. Let's just look at an example problem because I want you to see what this actually looks like with MCQs. All right, so we have a reaction. We are told it is not thermodynamically favored under standard conditions, but that changes as the temperature decreases. Which of the following is true at standard conditions? So when it comes to reading those multiple choice questions, everyone knows 60 questions, very little time. Time is money on this. So you don't want to waste time sifting through questions. So just try to immediately figure out what the question is asking. And it is hard, right? We are going to have a hybrid exam this year, but in Blue Book, you're going to still have all of the tools that you have had access to in other electronic tests that you've taken. You can highlight things, you can underline things, you can flag questions. Use those tools as you're going through those MCQs. All right. Yeah. All right. So now looking at this, and that's a great point. So learning that Gibbs free energy has to be negative. You can, exactly. And that's exactly what I think I have on my next slide. So you're going to use the Gibbs free energy equation to figure this out. So delta G equals delta H minus T delta S. Don't have to memorize that. It is on your formula sheet. Yes, that formula sheet is going to be electronic, but you can just pull that down and look at that if you need to. So if delta G has to be negative, how can you make sure that it still is? So we know that initially it's not thermodynamically favored. So I said thermodynamically favored conditions would be a negative delta H and a positive delta S. So we know that that is not the case. If we have the opposite of each of those, so if we had a positive delta H, a negative delta S, that is never favored. But now if we look at this equation, we can figure out how we could have a system where it is still favored. So if we're looking at this, we have to think, okay, if temperature is low, how is that going to impact? Right. And someone just asked, yeah. So it's got to be at so low temperature. We need them both to be negative. So we know our enthalpy is going to be negative. If delta S is negative and temperature is low, when we do this, we'll end up adding those to this. So as long as delta H is negative still, delta S is negative, we can still end up with a negative delta G. So you have to kind of think your way through that, walk your way through that equation. If you need to put arbitrary numbers in there, do that. You don't want to spend a lot of time on it though. So that's a hard thing with MCQs too, is you really don't want to spend a lot of time on it. So if you want to just memorize this, this is really useful. It tends to come up. So if you can remember that at low temperatures, negative delta H, negative delta S are favored. At high temperatures, all positive. And then just knowing what is always thermodynamically favored is always useful. Yeah. And it looks like you are putting some great tips in the chat too. There are all kinds of different ways to remember it. And yes, the periodic table, I have to tell you, the AP community has fought for a paper copy of that for you all. So you will have a paper copy of the periodic table in your test booklet. You can also get up to 5 pieces of scrap paper right away. So you will have scratch paper. So if you're someone who works on paper, I wish you could see my desk right now because I feel like my office just blew up. I have papers everywhere with little notes. If you're like me and you want that, you can have 5 pieces of scratch paper, and then you can ask for more if you need it. So you will have a FRQ booklet, you will have scratch paper. You can bring in your calculator. A lot of people have been asking me about that lately. Yes, Desmos is built in, but you can still bring in your calculator. And no, you do not have to erase the memory of your calculator. So I would just bring in the calculator you've been using all year long, right? Use what you are so comfortable with. Yeah. And Rose said, how much scratch paper do we get? 5 pieces. And if you need to, you can get more. Um, so can I rip the periodic table out of the packet? I would ask I would ask the proctor. You don't wanna do anything that's gonna jeopardize. But yeah, personally, I would wanna rip it out too so that you can just easily look back and forth. I promise we really tried to get the formula sheet on paper too, but I feel like getting the periodic table on paper was a win. All right, let's keep moving. So the next thing you really want to be comfortable with, and everyone knows it's going to be IMF. So I've had a lot of questions actually recently asking about determining IMF and things like that. So we'll practice a lot with that. So when it comes to IMF, know the difference between intramolecular and intermolecular. So IMF, typically we're talking the intermolecular forces, which are just going to be the interactions between particles. When it comes to chemistry, use the prefixes, use the suffixes to try to figure things out, right? Intra, that prefix means within. So we're looking at the actual bonds versus inter, that's going to be between particles. And we will talk about each of those in depth. So here's just like a breakdown of the main things you need to know with IMF, understanding the strength of intermolecular forces and understanding how that changes with the size of the molecule. And we'll talk more about all of this. But let's just start with the basics with IMF because you want to have a really strong foundation with that. So what types of intermolecular forces are you going to be expected to know? I have an image on the screen. Hopefully you can see this. I'm so sorry that my slides did not work out tonight. It's so frustrating. But what I want you to be able to do is identify these, and then we're going to talk about how we actually identify them within a molecule. So understand the basics, right? So the first one that you see there, that's going to be an ion dipole interaction where we have an ionic substance that has been dissolved in a polar solvent like water. So this is actually the strongest intermolecular force, but it's not the one you're going to see on most of your test questions because we're going to be focusing on polar molecules. So when it comes to a polar molecule, we're looking at a dipole-dipole interaction between those opposite ends of those dipoles. We can have a specific type, hydrogen bonding, that's a specific type of dipole-dipole interaction between hydrogen in an electronegative bond and a very electronegative atom, either oxygen, nitrogen, or fluorine. And then everything experiences London dispersion forces. London dispersion forces are just based on that random movement of electrons. So they randomly end up hanging out over here, leaving a partial positive wherever they are not. The strength of LDF increases with the size of the molecule. All right, so let's see. Yeah, so it looks like in the chat, can you explain ion dipole? Yeah, so when it comes to ion dipole, use the word, right? Use the, the term to figure it out. You're taking an ionic substance. This happens when an ionic substance is dissolved in a polar solvent. So most often you're going to see it with water. So if you look, I took sodium chloride, I broke that up into the chlorine ion and the sodium ion, and then the chlorine is going to interact with the oppositely charged side of the water molecule. So the negatively charged chloride ion is going to interact with the positively charged H plus ion versus the sodium ion is going to interact with the negatively charged oxygen. And I shouldn't say negatively, it has the partial charges, right? With those dipoles, polar molecules, you're going to develop partial positives and partial negatives. So that's basically what ion dipole is. You don't spend a lot of time with it because, again, it's not something that shows up too often on the FRQs or the MCQs, but you should understand what it is. All right, so when it comes to IMF, understanding polarizability, that is such a phrase. So what does this mean? It's just the tendency of the electron cloud to become distorted. So when that happens, right, when you have all of the electrons over here, you have a partial positive wherever they are not. So this is what LDF is based on. And LDF can be pretty strong. So the reason like geckos are able to scale walls and do things like that is because of these van der Waals forces. So don't think that they are just weak. They are still very strong intermolecular forces. But basically, these temporary dipoles are going to lead to stronger London dispersion forces. It's going to change how things react. It's going to increase the solubility in water. So it can be very important. So when it comes to polarizability, what does that even mean? Right? So, which one is going to have the more polarizable electron cloud? It actually couldn't be easier. It's based on the number of electrons it has. The size of the molecule is going to determine the number of electrons. The more electrons you have, the more polarizable that cloud. Because if I have a molecule that has 5 electrons versus one that has 15, right? When I have 5 electrons over here versus 15 over here and 15 not here, what's going to be the stronger interaction? It's going to be the one that has more electrons. So the more polarizable the cloud, the stronger those London dispersion forces. And hopefully you've done a lot of practice with FRQs looking at that, where you have to describe why something has stronger LDF. It's always going to be the size of the molecule and the polarizability of the electron cloud. Yeah. Okay. Yeah. And the other thing you really want to pay attention to, so these are the equations that are not on the formula sheet. So I have my students memorize these. A lot of these equations are just situations where you have rearranged the equation, like the log, right? Knowing that the H plus concentration is equal to 10 raised to the negative pH. But the thing is, you don't want to be moving logs around while you're taking the AP exam. You want to have those equations. Another big one is the one right next to that, K equals E raised to the negative delta G over RT. So understanding that, just memorizing these, this is the other thing I would recommend memorizing so you're just ready. This first equation is the big one. We'll talk electrochem in just a little bit, but understanding that the cell potential is equal to the cell potential at the cathode minus the anode, then you don't have to change the signs of any of those reduction potentials or anything like that. You just plug it in, you have your answer. All right. So let's just keep going. Yeah, unit 6 for sure. I know Austin just called me out. It's low key blurry. I could not get anything to load tonight. My presentation is too big that I can't even get to load, unfortunately. But you have access to all of these slides, so go ahead and grab that link from the description of this video so you have it and you can look at this. As I said earlier in the live, every time you see a little laptop or a screenshot of a video, that's a direct link to something to help you with the topics that I'm covering. So just get those notes so you have it. And I apologize. Yeah, will I be going over all of the units? Initially, that was my plan. I tried to go through things as quickly as possible, but I think I'm just going to hit on like the big ideas from each. And if you have any requests, yeah, unit 8 for sure. So you have it. All right, so things to know. These are some other things. Assume the 5% rule always applies. When it comes to equilibrium and ice tables, 5% approximation is just this idea that we're going to imagine that X is so small that we can just ignore it when we're doing like Ka or any of those equilibrium concentrations. So we don't have to ever use we don't ever have to do any algebra past the simple algebra. So we also want to use 3 sig figs throughout the exam. What does that mean? So with this exam, there might be one point on the entire exam that is designated as a sig fig point, where you're maybe looking at the volume of a burette, doing something like that. That is the only time you actually have to get the correct number of sig figs. Everywhere else, you have you can do plus or minus 1 extra sig fig. We have never seen more than 4 sig figs or less than 2, so 3 is a safe bet. When you are taking this test, you always want to check out all of the given units. So a lot of times, if you have no idea how to do something, a lot of students will struggle with like, delta H of fusion, the enthalpy of fusion, things like that, heat of vaporization. And you're like, I haven't done that at all, but I need to find my answer in kilojoules per mole. Guess what? Use those units to help you out. Same thing is true when you're looking at constants. Always look at the units in the constant to make sure they match up with all of the other values you're given. So you don't make a silly mistake and forget to convert your temperature from Celsius to Kelvin. So use the units to your advantage. I'm all for using the test to your advantage as well. You also want to remember that you're going to try to answer every single question. I don't want to hear about this incredible mole doodle that you left on your FRQs. No, don't waste your time doing that. Remember that error carries forward. So what that means is if you have a long FRQ and you have parts A through F, and you are struggling with part A to even know where to begin, but you look at part C and you're like, oh, wait, I know how to do that, but I don't have the value I need from the initial two parts. You can say, assuming the concentration is 2.4 molar, blah, 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 blah. If you do the rest of that correctly, you will still get full credit. So understand that everyone wants you to do well on this exam. So you got to just keep trying, and I don't want to hear that you gave up and just drew all over it or just wrote, I'm so cooked, I'm so cooked. You're not. Like, it's always worth it to go for those few points. You never know what's built into the test, and a lot of times I think you can surprise yourself with the amount of chemistry you actually know at this point in the year. Yeah. Let's see. All right, so let's keep going. Looks like we have a lot of questions. Yeah, molar enthalpy of fusion and vaporization. That's what I was just talking about. Well, how about we'll plan on talking about that? All right, what not to say. I just posted a video on this a couple days ago, but like, don't say like dissolves like, opposites attract. Don't talk about the arrows with trends, things like that. Actually describe what's going on. And it doesn't have to be an essay. You do not have to write essays in AP Chem. That's one of the nice things, right? Like, um, but you want to just remember that you want to describe what's happening. Yes, like dissolves like. What does that mean? That means that two polar species will be miscible. They will dissolve in one another because of the interactions between those molecules. Opposites attract, right? What does that mean? The positively charged protons are attracted to the negatively charged electrons due to Coulombic attraction, right? You want to actually describe what is happening. Same with trends. The radius is going to increase as the effective nuclear charge decreases and the size of the right, the electrons are not, that was not a good example, but you want to actually describe the trends that are happening. All right. So when it comes to periodic trends, I knew I was going to get into this at some point. Like I said, you don't want to describe the location of the atoms. Sulfur is located to the right of phosphorus, therefore it has a higher ionization energy. Yeah, you can draw in the arrows to help you remember those trends, but you want to actually describe why that's happening. Those arrows are just to help you memorize those trends, but you got to think it all relates back to the atomic radius trend. So sulfur is going to have a greater nuclear effective charge because it has more protons in its nucleus compared to phosphorus. Therefore, sulfur's valence electrons will experience stronger Coulombic attraction and will require more energy to remove. Okay, so the closer those electrons are to that positively charged nucleus, the harder it's going to be to disrupt that attractive force. And therefore, the higher the ionization energy or the energy required to remove an electron. When it comes to ionization energy, a lot of students ask about I equals 1 versus IE2. So when you're looking at ionization energies, the first ionization energy refers to the valence electron. As we see successive ionization energies past that, you're going to see a huge jump when you move from that valence shell to an inner shell. And that's going to be a great way to be able to identify an atom. I should have put in an example like that because that's something else. All right, let me hop back in the chat and see. Ionization. Yeah, Gus. So ionization energy is just the amount of energy required to remove an electron from either the valence shell or any of those inner electrons. It just depends. Typically, we're looking at the valence, the outermost electron first, but it's just the energy required to remove an electron from that gaseous atom. And it is opposite trend of atomic radius. So the bigger the atom, the further the electrons are from the positively charged nucleus, and the easier it is to remove. The smaller the atomic radius, the harder it is, and the higher the ionization energy. Yeah. All right. So this is the breakdown of all of the units. So if you've already downloaded this, and hopefully you have because it is so blurry, I'm so sorry. I would like for you to go ahead and you can use this as you're studying. Click on any of those and you'll jump right into the unit that you need. All right, so unit 1, hopefully you feel really confident with all of these. I would say these are the newer topics that students tend to struggle with: mass spec, photoelectron spectroscopy or PES, and periodic trends. So feeling really confident with those is important. So take some time to review those topics if you have not already. So mass spec. So if we have a mass spectrum, you want to be able to identify the average atomic mass of the element and the likely identity of the elements. This should be easy points. Sometimes we'll see these on FRQs too. So if we're looking at this, oh, see, you're not even going to see any of the text that I added. All right. So we're looking at this and you're like, oh, wait, why is my percent abundance greater than 100%? What am I going to do with that? You're going to breathe and you're going to realize it doesn't matter. I'm going to add up my totals and I'm going to still figure out the percent abundance. So instead of a percent abundance immediately giving me my percentage, I'm going to say, all right, I have one that has a relative abundance of 25 and one that's at 100. So out of my total, the first isotope has a percent abundance of 0.2 versus the second has a percent abundance of 0.8. If I want to then find the average atomic mass, it is still the same process now. So it's the mass times the percent abundance of each isotope, add those together, and you will have that. You can then use that mass to figure out the likely identity of that element. Go to your periodic table, find the average that is closest to that one, and you should have it. So this one, in case you haven't seen it yet, so even looking at this without doing any math, I can say, all right, 80% is a mass of 11, only 20% is a mass of 10. That's going to be closer to 11. I look at my periodic table, I'm looking at boron, let's see. Yeah, so 10.8 is the average. That should be boron. Yeah. All right. So let's move on. Let's see. So this is just, yeah, I don't think we need to do that. No one's asked about that tonight, but this just help with empirical molecular, all of that. All right. Apparently I don't have any PES in here. I'm so sorry. All right. You know what I might do? I might just upload my slides from last year's so you have those as well. All right. So photoelectron spectroscopy, things to remember with that. You want to make sure you are remembering with the chart. Sorry, that's going to throw everyone if I'm just like flipping through those. You want to make sure that when you think about your photoelectron spectroscopy, when you think about the spectrum, the axis, like the origin, is the nucleus. As you move out from that, you are moving away from that. So you want to remember the nucleus is here, and then you can identify each of those electrons from there. So as you see those peaks, you'll see the 1s2, 2s2, 2p6. You'll just then label from the left to the right, and that should be all that you need for PES. Occasionally with photoelectron spectroscopy, we'll also see changes in that, and we'll have to describe what's happening. Again, remember, this is your nucleus, and then we're moving out from there. So as we see those changes, what are those indicating? Which one is going to have the higher energy? All right, I wish I had included an example for that. I am so sorry. We're going to keep moving. All right, when it comes to two, I've seen a lot of questions tonight in the chat. How do I determine whether a bond is polar? What do I do when a molecule has multiple bonds? Where do I go from there? Yeah. Okay. I will, you know what? I will update the slide links so that you have all of the PDFs and whatnot too. I'm sorry about that. All right. Yes, and yes, you do need to know IMFs. You absolutely need to know IMFs, and we can talk more about that. Yeah. All right, so let's go from here. So polar versus nonpolar covalent bonding. If we just look at the basics, right, we're looking for a difference in electronegativity. This is electronegativity trend. If you don't have access to that, you're going to be looking at the location of each of these atoms. So fluorine is going to be your most electronegative as we move away from fluorine. So hydrogen versus fluorine, you'd expect to see a significant difference, and that is going to be a polar bond. So we're looking for just something that is greater than 0.4. Know that the carbon to hydrogen bond is always nonpolar. But then from there, we can then figure out whether a molecule is going to be polar. So you determine the polarity of each bond, and then you look at the overall molecule. So what do I mean by that? You're going to look at the symmetry of the molecule. So if I had CCl4, carbon to chlorine is a polar bond. But because I have a tetrahedral molecule, like this one, all of those vectors essentially cancel out. All right. So if you have a symmetrical molecule, even though it is polar, it will be nonpolar overall. If you have something that has a lone pair, let's say we have something that is trigonal pyramidal, it is no longer symmetrical. This would be a polar molecule. If you look at the example on the screen right now, we have CH3Cl. That is not a polar molecule. That carbon to chlorine bond is going to be polar versus the carbon hydrogen bond is not. But because we have the electronegative chlorine pulling those electrons toward itself, the overall molecule would be polar. All right. So that's what you want to do. You want to look at the symmetry of that. That's how we're going to then determine all of the IMFs coming from there. When it comes to lattice energy, you're remembering Coulomb's law. I don't know why I said it that way. Coulomb's law. You're looking at the magnitude of charge versus the distance between those charges. So the smaller charges are actually going to have higher lattice. So the smaller atomic radii are going to have higher lattice energy because charge again is going to be directly proportional to the magnitude of charge and inversely related to the distance between those charges. So the closer those charges are to each other, the stronger that attractive force. Let's see. Molecular geometry is the death of me. I know everyone feels that way. It's okay. You just have to memorize those. Thankfully, you don't need to know the bond angles or anything like that, but know how it changes, right, as we're adding atoms and lone pairs to that central atom. Yeah, redox titrations. No, you don't need to know. Well, you might have to do redox titrations, yes. Sorry. The AP exam is on Tuesday. Yep. Okay. All right. Sorry, I'm just having too much fun reading the chat. All right. When it comes to Unit 2 is not a difficult one, but occasionally we will see FRQs where all of a sudden they're going to throw in vocab that you have never seen. You do not want to be thrown by that, right? If we're looking at alloys, substitutional alloy, what does that sound like? Sounds like we have an atom that is substituting another one, and that's exactly what it is. Versus an interstitial alloy, you have atoms coming in between. So again, don't get intimidated by the vocab. Pull out what you know and then work your way through because those shouldn't be too tricky. Let's see. All right, another thing that's been coming up a lot is just understanding resonance and formal charge. So resonance is just this idea that you're going to have multiple Lewis structures that are possible, and then we're going to use formal charge to actually decide which one is the best structure. So which one is actually going to be favored. And that's going to be based on the formal charge. So to calculate formal charge, the easiest way to remember it, it's the valence minus the dots minus the sticks. What I mean by dots, lone pairs on that atom, and then the sticks are the bonds. Or you can remember bonded electrons divided by 2. I think valence minus dots minus sticks, easiest way to do this. So if I'm looking at this ion and I want to calculate all of the formal charges. Again, let's look at sulfur. So sulfur has 6 valence electrons. If you see there are 6 dots around that sulfur atom, it's going to be really hard for you to see. I apologize. And then we have a single bond, so 1 stick. So that means it's going to have a charge of -1 in that first structure. So we can then go through and calculate all of the formal charges of each of these atoms. And then what you want to do is you want to compare all those resonance structures. What are you looking for? You're looking for the smallest magnitude of charge. You also want to make sure that the charge matches the charge of that compound. So in this case, we have a polyatomic ion. It has a negative charge. It has an overall negative charge of 1, which all of these do show that. So that's good. But then you also want to make sure that the most electronegative atom carries the most negative charge. So in this case, we would say that the second structure is going to be favored because it chose nitrogen with a charge of -1. So that's kind of how we look at resonance and use formal charge to decide which structure is favored. Yeah. So again, look for a small magnitude. You don't want to have +4 on one side, -4 on the other. Not a good idea. And then you want your most electronegative atom to carry the electric charge. The negative charge. It's been a long day. And then someone was just talking about in the chat, what do we do about Vesper, right? You have to memorize them, unfortunately. The expanded octet, yeah. So you just have to start with the Lewis structure. From there, you can then count the number of bonds to that central atom plus the lone pairs, and then go from there. Yeah. So of the things you have to memorize so far that we've talked about, memorize the things that are not on the equation sheet, memorize the conditions that are thermodynamically favorable, and You gotta memorize the molecular geometries. I'm sorry. All right, and when it comes to hybridization, I've had a lot of questions coming in about this as well. This is basically hybridization. We are mixing orbitals. So I like to refer to it as mixing paint. You take blue and pink and you mix them together. You can see a little bit of each color in that final product. Same thing is true with bond hybridization. When we're mixing orbitals, it's going to be a blend of whatever orbitals we have mixed. But the good news is it's really easy to actually write out the hybridization. When you are figuring out the bond hybridization, you are just counting the number of bonds and lone pairs to that atom. Okay, so if I had, in this first example, I have BeCl2, so we have beryllium with 2 chlorine atoms on either side of it. We're looking at beryllium. It doesn't have any lone pairs, it just has those 2 bonds. So therefore, it would just be sp hybridization. And just like with everything in chemistry, right, we're not going to show ones if we don't need them. And it just moves on from there. So just count the number of bonds and lone pairs to that atom. You can only figure out the hybridization of a single atom. And then it's actually just a really easy point, thankfully. Yeah. All right. So looking at this, this is from my friend AP Bio Penguins. So this is a compound that was actually synthesized because it looks like a penguin. I know chemists are fun like that. But let's say if we're looking at carbon 1, it has 3 bonds to it. So we'd say that that is sp2 hybridization because remember S is 1 plus 2 gives us those 3 bonds. If I look at carbon 2, it's kind of hard to see, but we have 1, 2, 3 bonds. That would also be sp2 hybridization versus carbon 3. Looks like we have a bond to carbon and then 3 bonds to hydrogen. That would be sp3 for 4 total bonds. All right, so that, again, we see this every year on the FRQs. That's a guaranteed easy point for you. Just be able to count the bonds. All right, other thing you might see is sigma versus pi. Sigma, think single bonds, but actually everything has a sigma bond. So sigma and pi orbitals just refer to that mixing the hybridization. If you have a double bond, you're going to have a sigma bond and 1 pi bond. If you have a triple bond, you're going to have a sigma plus 2 pi. So if I wanted to look at this molecule, I could count up all of the sigma bonds. Guess what? Every single bond in this molecule contains a sigma bond plus the pi bond. So I'd be pulling out the double bonds here. So I'd say I'd have 3 pi bonds plus however many sigma bonds this is. All right, so this is just a structural formula to show that. We're not going to spend time on that. All right, getting into Unit 3. Unit 3, everyone knows this is worth up to 22% of the exam. Everyone was really upset last year because there wasn't a lot of IMF on there, but that's because Unit 3 is not just IMF. You have gases, you have solids, you have the ideal gas law, solubility, spectroscopy, Beer's law. There's a little bit of everything in this unit. So let's talk about IMF again. So when it comes to IMF, ion dipole interactions, this again is the one that you're exposed to least in class, but it really is really simple. So when you have an ionic substance, you dissolve that in water. Guess what? The ion is going to interact with the oppositely charged side of the water molecules. So the positive sodium ion in this case is going to interact with the partial negative on the oxygen atoms. This is actually the strongest intermolecular force, and this is why those ionic substances will form the electrolyte solutions, right, allowing the flow of electricity through. But again, it's not one that we see very often because we're more focused on seeing how those dipole-dipole interactions and hydrogen bonding and how those sites impact all of those physical properties. So when it comes to dipole-dipole interactions, you need to be able to identify first, is it a polar molecule? So dipole-dipole interactions are just interactions between polar molecules. And the strength of this interaction is going to increase with increasing polarity. So the more polar the molecule, the stronger its dipole-dipole interactions. Why? Because the greater the difference in where those electrons are found, right? So a polar bond is just a shift in the density of the electrons towards that more electronegative atom. If you have a very significant shift, that partial positive, partial negative, that's going to form a stronger interaction between those. Yeah. All right, versus hydrogen bonding. Hydrogen bonding is just going to be a specific type of dipole-dipole interaction. How do you identify what experiences hydrogen bonding? It's easy to say, okay, it's going to be between hydrogen and a very electronegative atom. So you're looking for oxygen, nitrogen, or fluorine. But the key here is that hydrogen has to be in a polar bond. Okay, so if you have only just carbon to hydrogen bonds, you're not going to experience hydrogen bonding. Hydrogen has to have a partial positive charge for this interaction to occur. So make sure that hydrogen is in a polar bond and then it's interacting with a very electronegative atom. And there can be multiple sites, and we'll look at a practice question with this versus London dispersion forces. Again, everything experiences LDF or London dispersion forces, and the bigger the molecule, the stronger the LDF because of the polarizability of the electron cloud. We talked about that earlier in the session. All right, so how do I identify IMF? You're looking to see, okay, do we have ions present, right? If we have an ion, then we can have ion dipole interactions. Next up, you want to ask, are the molecules polar? If the molecules are polar, expect dipole-dipole interactions. Let's take that one step further. Do we have hydrogen in an electronegative or polar bond? Okay. And do we have oxygen, nitrogen, or fluorine? Yes. Okay. If we do not, it has only LDF because guess what? Everything experiences LDF. Yes, even nonpolar molecules experience LDF. All right. So let's practice with that. So this is dopamine. I want to know which IMF is dopamine going to experience. Yeah, so nonpolar molecules can only have London dispersion forces. Good job. Yeah. And strong acids have come into the chat. All right. So looking at this right away, I see this is an organic molecule. It is carbon based. We have carbon, oxygen, hydrogen, and nitrogen in there. So now looking at this, it's like, oh, wait. Okay. I know we don't have an ionic substance. So definitely not ion dipole. But is this polar? Yes. We have oxygen to hydrogen, oxygen to carbon. We are going to have some polar bonds here, and the nitrogen to hydrogen bond is polar as well. So we know we're going to have dipole-dipole interactions. Guess what? We are also going to have hydrogen bonding at those sites. So we do have a few instances where hydrogen is going to have that partial positive charge. It's going to interact with either oxygen or nitrogen. That nitrogen down low is going to be hard to get to, but could happen. And then it's going to experience LDF because everything experiences LDF. So those are kind of the questions you want to ask as you're trying to decide. This is an FRQ to show you what the problems look like. Maybe you've seen this one before, but this one will actually tell you the same three types of intermolecular forces exist between both of these molecules. But why is the melting point of salicylic acid or aspirin higher than that of the other one? So you're like, oh, wait, okay. So they're both polar. They both experience hydrogen bonding and LDF. Now what, right? You want to look at the molecules. Thankfully, they already have the structural formulas there for you. Find those acidic hydrogens. Which hydrogens are going to be involved? Where am I going to have hydrogen bonding? Because that's what's going to determine the difference. So looking at this one now, we know, again, this is what's given. How are these structures different? If we look at the first structure, we only have that one hydrogen versus salicylic acid. We have two locations that we can then experience hydrogen bonding. So because we have two sites in the second compound, this means it's going to experience stronger IMF. The stronger the intermolecular forces, the stronger the physical properties, right? So the higher the melting point, the higher the boiling point. The only difference is it's going to be the lower the vapor pressure. That's the only exception. But the stronger the IMF, the stronger we expect all of those other forces to be. Because why? Why will it take more energy for this to melt? Because we have more interactions between the molecules that we have to disrupt before we can shift from the solid to liquid state. So it all ties back to that. All right, let's see. Yeah, how do you tell which hydrogen is most likely? You want to look for the ones that are kind of hanging out by themselves. Never anything attached to carbon. It's going to be attached to oxygen or nitrogen, and see how these ones are just kind of open and off to the side. Those are the ones you're going to be looking for. Yeah, there's a lot that goes into that. It's a lot of organic chemistry, but for the purpose of AP Chem, again, you were looking for the one that is kind of like sticking out like a tail almost. That's going to be the one that's going to pop off when it comes to acidic hydrogens. All right, so that's like the big thing. Ideal gas law, and yeah, okay, let's talk about KMT. So when it comes to ideal gases, understand that when we make some assumptions, we're using the ideal gas law, and that's that the particles of gases experience no attractive or repulsive forces. They just have no IMF. They don't interact with each other whatsoever. Not really the case, right? We're also going to assume they have no volume and they're going to be moving completely randomly. And whenever they do collide, it's completely elastic. It's like, no big deal. There's no transfer of energy. What do we need to know? You need to think about what happens when we deviate from ideal behavior. So most ideal, easiest way to remember this is plight. Pressure is low. ideal gas, high temperature. Versus least ideal is going to be the opposite of that. High pressure, low temperature is where we're going to see the greatest deviation. So another thing to add to the list of things to memorize for the exam on Tuesday. All right, another thing you want to be really comfortable with is the Maxwell-Boltzmann distribution. We tend to see this every year. And where students struggle is you look at this blue peak and you're like, whoa, that's a lot of particles, right? So you see this, you're like, okay, that's a ton, that's like much higher energy, right? No, not the case. If you look at the temperature values, it's actually the opposite. So you have to read your axes. And this is a really great point when it comes to the FRQs and the MCQs. Take a second to read your graph because your graph is going to give you a lot of information, whether it's giving you the units or the description that you need. Take the time to read your graph. So in this case, this one is showing us the number of particles. As we get to higher temperatures, the speed, there's a greater difference in that speed. Um, the tall peak is not more particles. Sorry, I don't know why I said it's not. Look at me. The taller peak is not a higher energy. So be careful. Recognize that that just represents the number of particles at that speed. Okay, so there's an increase in the variety of particle speeds as the temperature increases. And that's what we see with the Maxwell-Boltzmann distribution. So be able to interpret this, explain what's happening, be able to predict which one shows which temperature. So we always start with a low temperature as we increase the temperature, the kinetic energy increases, and that's why we see a greater variety in those particle speeds. All right, this is the other part of 3. I feel like, okay, solubility, that's another big one. So what do you want to know when it comes to solubility? Focus on what's always soluble. Don't memorize any of the exceptions, anything like that. Know that group 1 ions, so sodium, potassium, always soluble. Ammonium, nitrates, and acetates, always soluble. So if you can remember what's always soluble, you will be set. All right. Another thing when it comes to solubility and all of that, I've been mentioning these quite a few times, but know the polyatomic ions. It's just going to save you so much time. They're common ones. I think I linked a quizzes in here or a Quizlet. You can look them up. Just memorize those common ones if you haven't already. I'm sure you have at this point in the year. You're like, that's light work. I got this. Yeah. All right. So let's keep going. So unit 4 is, I feel like that's the really easy stuff. Let me know if you're not. Okay. No, if you all collectively fail, they will not give a high curve. Sorry. If only it were that easy, right? You're going to be fine. So this is all just basic stuff, unit 4. Hopefully you feel really confident with that. Stoichiometry should be really easy. And you know what? I think it's hard because like you see this and you're like, this is so easy compared to what I've been doing. But we see it every year in multiple spots. I want to say last year we saw it in like 2 or 3 questions. Just know how to do simple stoichiometry to get those easy points. Yeah, okay, oil rig, we can go over that. Let's do some redox because I think that's the hardest thing in unit 4. All right, so when it comes to redox, there are a whole bunch of mnemonics that help you with electrochem, like oil rig. So remembering the oxidation is loss of electrons, reduction is gain. So in a redox reaction, right, it's the transfer of electrons, exchange of those electrons. It's all counterintuitive when it comes to electrochem. That's what makes it hard, right? You're gaining electrons to become more negative, but that's why these mnemonics are really helpful. All right, so let's just balance one. So what you want to do first is you want to write out all of the charges of the half reactions. So you can either do that underneath with brackets, or you can just keep track above the reaction. Anytime you have a pure solid, that's going to have a charge of 0 versus the ions. Obviously, it's indicated, which is really nice. So for example, we have the charges of each. Then we want to figure out what is going on. Are we gaining or losing electrons? So again, it is counterintuitive. If I look at aluminum, I'm going from 0 to +3. That means I have actually lost 3 electrons. So we're going to give those 3 electrons as products versus Cu2 plus to Cu just solid. We're going from 2 plus down to 0. So that means that we are gaining 2 electrons there. So you want to write out those half reactions, and then your goal is just to get the electrons to cancel out. I feel like this is so much easier to do at a whiteboard. I apologize. I'll do redox tomorrow night with my tech live so you can actually see this. But basically, you balance the half reaction. Looking at this, I see that my electrons are not balanced out. So I want the electrons to cancel out. I'm going to multiply the first one by 2, multiply the second one by 3, add those 2 together. all of the electrons cancel out and it is balanced. Let's see. I don't know if that's, yeah. All right. So let's move on to unit 5. I really want to spend some time on the bigger ones, and I feel badly that we've been going so long. All right. So unit 5, another thing you want to add to the list of things to memorize is just these rate laws. So there's always a multiple choice question where you're given the rate law, information has been graphed, and all you have to do is look at the graph, figure out which slope is linear, and then you have the order of the reaction. So understanding if we're just looking at concentration over time, that indicates a zero order reaction. The concentration does not impact the rate at all. Versus for first order, we're looking at the natural log of A over the time, versus second order, it's going to be 1 over the concentration. So look for that linear curve. Know that the slope is going to be equal to the rate constant. When it comes to rates, rate is going to be equal to that rate constant times the concentration of the reactants raised to the power of the coefficients. So the rate is just going to be based on the disappearance of those reactants over time, and that's all it is. So it's really not as hard as a lot of the stuff that you've been doing, but again, it does help just to memorize these things just to make it easier. And when it comes to rates, with the rate constant, you do have to give the right units if you're asked to calculate that. So be really careful with that, whether you're given data from reactions or whatnot. You want to just make sure that you are being really careful with those units. Again, you can memorize it if that's something you struggle with, but as you're doing the calculation, if you're just careful about actually writing in your units at each step, you should get the right units. All right. All right, let's move on to unit 6. Thermo. This is all the basic stuff. I haven't seen anyone asking about thermo. Yeah, rate law is just based on the reactants. Yep. Yeah, and there's no third order in AP Chem. Nope, we just stop at second order. All right, let's do, okay, we haven't done any lab-based practice. So let's do a sample MCQ. So let's say we're looking at a calorimetry experiment. And during the experiment, the student forgot to put the top on top of the cup. So let's say we're looking at a coffee cup calorimeter. Um, and how would this affect the calculated value for the metal's specific heat, or C? So when we think about heat transfer and calorimetry, right, we're using Q equals MC delta T. Basically, this idea that the heat lost is equal to the heat gained. So we have a metal that we're dropping into water. We're measuring that. We're just setting up Q equals MC delta T for each. A lot of students are really stressed about the signs. Don't stress about the signs. If you think about your change in temperature is always going to be the final minus the initial. That alone is going to take care of the sign of the heat for you. It's not like we have negative heat. This is describing the transfer of heat. Was heat lost or gained by that specific system? So don't stress about that. All right. So looking at this, when you have a calculation, like, yeah, lab-based questions are the worst. Everyone feels that way, right? Because you're like, how am I going to interpret this? Expect to see one. And when you see your lab-based FRQ, you're going to have to just like subtract the mass of the crucible or the mass of the beaker. That's going to be like 1 point. So you're going to be just subtracting to get the mass of something. You're going to probably be converting that into moles. You're going to be graphing something or looking at a graph of the data and going from there. They are not as bad as you think. Maybe you're going to take a volume measurement on a burette. You're going to look at the burette and you're going to say, oh yeah, I know that it's exactly this, but I'm going to estimate 1 digit smaller. The lab-based questions are not as bad as you think. These ones can be tricky though, right? When you have to make predictions. So we want to look back at this. So we're looking at this and we have to think through step by step. If I don't put the top on the cup of my coffee cup calorimeter, how is that going to impact everything? What does that mean? Is my temperature value, how is that going to change? All right. So if I don't have the top on, it's not a perfectly closed system. So that means that some of the heat is going to escape to the surroundings, which means what? Means the change in temperature is going to be smaller. So if the change in temperature is smaller, how is that going to impact C? So you want to think step by step. How is this going to impact my calculation? If you need to, like I said earlier, throw some numbers into it. Just put a couple numbers in, see how that changes everything, and then go from there. So in this case, the calculated value is going to be too small because of that heat lost to the surroundings. Other things someone asked earlier about heat of fusion versus heat of vaporization, understanding just how to calculate this. A lot of times you'll be given the heat of fusion and asked to figure out like how much, or you'll be asked to find, like if you have 5 grams of something, how much heat will be released. Use the units to your advantage. Sorry, I'm running out of losing my voice already. All right. Yeah. Okay. So bond enthalpies, when it comes to enthalpy, enthalpy is typically products minus reactants. The exception is with bond enthalpies. So we're going to be looking at the energy of the reactants minus the products with bond enthalpies. But for delta H, delta S, everything else, it's always products minus reactants. So just know the difference. And the higher the bond enthalpy, the stronger the bond. And know that like triple bonds, makes sense. Triple bonds are going to be shorter, they're stronger versus double bonds where you only have 4 shared electrons, not as strong versus single bond, 2 shared electrons is going to be longer and not as strong. All right. Let's see. So this is just an overview of thermo. Again, this is all just kind of related back to what we were talking about with thermodynamic favorability, understanding that when it comes to thermo calculations, these are pretty straightforward. Don't make any silly mistakes. Take the time to actually calculate the sum of your products versus your reactants and then subtract those so you don't make a silly mistake. And then again, remember, bond enthalpies is the one exception with this, where it's going to be the sum of the bonds breaking or the reactants minus the products. All right. Hess's law, you're just adding things up. You got to think about it as solving a puzzle. And then making sure that if you flip a reaction, if you multiply a reaction, you're doing the same thing to your enthalpy. Okay. Yeah, let's do this. All right. I want you to take a second to try this one out. So we have the heat of vaporization for NCl3 is 32.9 kilojoules per mole. You want to calculate the amount of energy required to vaporize a 15-gram sample of NCl3. And you're like, how do I even do that? Right? I have no idea. No idea. All right, when it comes to this, you know already, you're looking at this, you're looking at your units, you're given 32.9 kilojoules per mole. What am I going to do? I'm immediately going to change my gram sample from grams into moles. And guess what? On the exam, you're going to be given most of your molar masses. It couldn't be easier. I'm going to take 15, divide by that 120 to figure out how many moles I have. All right, now I know that I have my delta H vap, right? My heat of enthalpy of vaporization is 32.9 kilojoules per mole. Guess what? I am literally just going to take 32.9 times my moles and I will get my answer. Don't ever forget to use your units to your advantage. If you have no idea how to figure this out, the amount of energy, I'm already given that constant. It's kJ over the moles. If I then just multiply by the moles of that, the moles cancel out and I'm just left with kilojoules. Yeah. All right. Okay, I'm just ignoring the drama in the chat. I'm sorry. We don't have time for this. We don't have time for drama right now at this point in the exam. All right. It's like my approach as a teacher, too. It's so bad. So bad. All right. Unit 7. This is where things actually get hard. I should have gotten to this like 30 minutes ago. I apologize. And by the way, 7.9, that should say Le Chatelier's principle. All right. So equilibrium. What do you need to know? Does not mean you have equal amounts of anything. Hopefully you do not have that misconception. It's when the rates of the forward and reverse reactions are equal and the concentrations of the reactants and products are unchanging. Can you have a situation where the concentration of reactants and products are equal? Yes, in which case K is going to be equal to 1. That's not normally the case. It just means you get to this point where those concentrations are constant. All right. Understanding, we talked about this earlier, reaction quotient versus equilibrium constant. Know that any of these constants, any equilibrium constant is going to be temperature dependent. So be really careful with that. But with reaction quotient, we're using that to determine where the system is. Are we approaching equilibrium? Are we favoring the forward reaction, the reverse reaction, or is Q equal to K where we are at equilibrium? Okay. And when it comes to writing the equilibrium expression, this should be the easiest thing, and you will absolutely see this. So equilibrium expression is always concentration or pressure of products over the reactants raised to the power of the coefficients in that balanced equation. So when it comes to that equilibrium expression, it is the one case where you don't have to actually have units associated with your answer, which is so nice, right? At least we have one situation where you don't have to include units, but it's always products over reactants raised to the power of the coefficients, ignoring any solids or liquids. If K, like we said earlier, if it's a large K, forwards favored versus a small K, reverse is favored. All right, let's finally get into rice or ice tables. So let's just jump right into it. an example. So given the initial concentrations, find the equilibrium concentrations for each of these reactants in this reaction. So we are given the K value. Say this is our Kc, and we just want to figure this out. So when it comes to these ice tables, you want to start with whatever you are given in the problem. And I just put out a video showing 3 different types of ice tables. This is the easiest type. All right, so we have our initial concentrations. We're assuming we don't have any product initially, so we're going to have a 0 there. Because we are starting with no product, right, we're going to be forming product. So our change, we're going to be subtracting from A, subtracting from B, and adding that to C. But if you notice, we have a coefficient of 2 in front of C, so we'll be adding 2x to C. So you subtract based on the coefficients, and then you're going to be subtracting or adding based on what's happening in this reaction. Let's say I had concentrations for each of the reactants and the product. I'd then have to figure out the Q. So you'd have to use Q to figure out what was favored in that reaction. So is Q less than K? Is it greater than K? Am I actually going to be going in the opposite direction where I'm making reactants? So that's the difference between that style problem versus this. So if you're given initial concentrations and you know you have no product, this is how you do it. You subtract X, you add it to your product. All right, and then you just add up those 2 rows, right? And you get your equilibrium. So if you notice, I have then gone on to calculate Kc to then calculate X. What have I done here? So I have applied the 5% rule. So the 5% approximation is just this idea that if you look at this first column, it should technically be 0.3 minus X. But in AP chemistry, we can always ignore X. So you're going to essentially assume that X is less than 5% of this initial concentration, and therefore it's not really going to impact my answer. I'm not going to ignore X over here. I don't know what I did. Yeah, I'm not going to ignore X over here, right, where I'm actually forming the product, because X is all of the product that I'm making in this case. So then we're just going to solve for X, and that's going to be our equilibrium concentration. When you're doing these problems, right, this process is pretty easy. Start with what you're given, look at the change, add those 2 together to find out your equilibrium concentrations. Don't forget to go back in after you've solved for X. And for example, the concentration of C is 2X. Don't forget to multiply by 2 and then write out the concentration, the equilibrium concentration of C is blah, blah, blah molar. Be careful with that. You don't want to make a silly mistake and do all of that work and then forget to actually find the equilibrium concentration. Yeah, so X is, oh yeah, so in chemistry, AP Chem, yeah, you can always ignore X. Does that feel good to know that that's the case? Yes. Yeah, and you actually don't have to show your work for the 5% rule. You do not even have to say, assume the 5% rule applies. You just go for it. You just assume it, and you don't even need to mention it. Yeah. So in class, that might not be the case. And I would say, as a teacher, I prefer to have my students mention it and talk about it. But on the AP exam, yeah, no matter what, X is something you can ignore. Yeah. So the 5% rule is just an approximation that says 5 is, so it just says that X is so small that it's less than 5% of the initial concentration, and we can essentially ignore it and still get pretty accurate answers. All right, another big thing from equilibrium is understanding Le Chatelier's principle. It's really easy to understand how concentration changes will impact a reaction, not as easy with pressure and temperature. So if the pressure decreases, the reaction is going to shift to favor the side with more moles. And this is only in the case of a gas. If the pressure increases, we'd actually shift to see whichever side has fewer moles. And how am I figuring out the moles in the reaction? You're just looking at the coefficients in the balanced equation. So if you have 2N2 on one side versus O2 plus, I don't know. I don't know why I'm 2NO2 on one side versus 1O2 plus, that's not great. Okay, I'm not going to try to make up an example on the spot at this point. But you're just counting based on the coefficients of that balanced equation. If you have equal moles on both sides, changes in pressure are not going to actually impact the system at all. All right, and then when it comes to temperature, you need to know whether it's an endo versus an exothermic reaction. Is the heat a product or a reactant? That's how you're going to determine that shift. And know that actually catalysts do not impact equilibrium, concentration of solids. Do solids have a concentration? That's a big question. Or liquids do not actually impact equilibrium at all. The only thing that really does is going to be temperature. All right, so KSP is the other big thing. VS Python, you don't have to memorize ionic compounds. Yeah. All right. So KSP, or the solubility product constant. When you're thinking about this, we're basically using this to figure out whether or not that precipitate is going to form. So to do that, you will be making another ice table, where basically we're going to use S, which is just the molar solubility. We're either subtracting or adding that. But because we're starting with a solid, you can just ignore that first column. So it looks a little bit different. But you actually don't have to do this. What you're going to do, you're going to add this to your list of things to memorize. And when it comes to KSP, you're going to think about the ratio of those ions in that compound. So if it's a 1-to-1 ratio, it's just going to be S squared. If it is a 1-to-2, that's going to be 4S cubed. It's rare, but if it's a 1-to-3 ratio, it's going to be 27S to the fourth. So when it comes to KSP, that's what we're looking at. Yeah, everyone hates ice tables. It's okay. That's like that. Yeah, everybody feels that way. Yep. All right. And no, catalysts do not affect equilibrium, do not affect equilibrium. Yep. All right. So that's when it comes to KSP. So let's actually look at a problem. So if we wanted to solve for S with a molar solubility, um, sorry, and this one I had a molar solubility of S equals 0.14 grams per liter. Let's see. We're actually gonna skip that. That does not look like a good example. You know what I'll do? I'll link a KSP video in the video notes, so you have that as well. I apologize. And I will plan on doing one live tomorrow night with Chig when I'm at my whiteboard, and it's so much easier, and I don't have a streaming system that doesn't want to upload slides. All right, acids and bases. So everyone is still stressing about this, and I get that. Acid-base chemistry is hard. Know that, yes, it is the second highest weight on the exam, but even though you can expect to see 8 to 10% of the exam is acid-base chemistry, the nice thing is it's not all going to be, weak acid, strong base titrations. You're still going to have some of those elementary ideas that you learned in Chem 1 even that will show up. And I'd say focus on that too, right? Make sure you feel really confident with the basics. You understand how to identify the acid base, the conjugate acid base pairs. You understand what's going on with these dissociation equations. And just being able to write those dissociation equations is actually pretty valuable. This is not great. Sorry, nothing worked. I spent all this time on cool animations and everything. That's how it goes. Anyway, biggest misconception when it comes to acid-base chemistry, understanding the difference between strong and weak acids or bases. What makes an acid strong? Is it that it has a really low pH? Is it that it's really dangerous, like hydrofluoric acid, that etches glass? It's neither of those, right? It's how much it dissociates in solution. If it dissociates or ionizes 100%, it is strong. And there are 7 strong acids that you want to have memorized. So a strong acid or a strong base is just something that completely ionizes. So hydrobromic acid is one of the 7 strong. It just means that you put it in solution, it's all going to separate out into H plus and Br minus versus HF. HF is a very dangerous acid. However, it is not classified as a strong acid because it does not fully ionize in solution. And we're going to use the percent ionization to figure out how strong or weak those acids are. But these are the 7 strong acids to memorize. These are the strong bases. The strong bases are a little bit easier because it's going to be the group 1 and group 2 hydroxides, basically. Those are going to be your strong bases. All right. So again, strong means that they dissociate, not that they're dangerous. So just be really careful with that. Yeah. Yep. And we will definitely do titration curves. No, please don't drink 10 molar HCl. No, not a good idea. So the reason your throat hurts after you get a stomach bug or you start throwing up is because we have hydrochloric acid in our stomachs, right? So just when you throw up, that acid eats the lining, and that's why you have a nice sore throat after, right? So no, I'm not going to recommend that. No, thank you. All right, so let's keep going. Okay, so conjugate acid base pairs, right? If you can look at this and hopefully identify the acid, the base, and their conjugate pairs here. So the base is going to be the hydroxide. It's kind of easy to identify with this one. The strong base is potassium hydroxide. The weak acid is the next one. What happens, you have to imagine this hydrogen ion is a moving hydrogen ion. That H plus pops off, reacts with the base to form the conjugate acid, leaving us with whatever the acid becomes. It's the conjugate base. And when it comes to those conjugate acid base pairs, remember that the weaker the acid, the stronger its conjugate base. conversely, right, the stronger the base, the weaker its conjugate acid. So they're going to be opposite in terms of the strength. Just a little nuance to know. Let's see. See, now everything has all of the answers too. All right. So when we're thinking about pH. Everything with strong acids, strong bases is really easy, right? If I'm doing a titration with a strong acid, strong base, the equivalence point is going to be right at 7, like no exceptions, right? Versus if I'm starting to work with weak acids and strong bases or weak bases and strong acids, it gets a little bit more complicated. But let's say I want to just find the pH of a strong acid. The strong acid completely ionizes in solution. So that means that it's going to change completely into H plus, and the concentration of H plus is going to be equal to the initial concentration of that acid. So when you take the negative log of that, it's just the negative log of the initial concentration of the acid. It's really easy. It's a little bit more tricky with a strong base because you just have to take it one step further. So you have to remember, right, that the POH plus the pH is equal to 14. Be really comfortable with just subtracting and remembering that. I feel like a lot of students, you get so in depth with acid-base chemistry that you forget the basics and you forget to be able to do that. Okay, don't forget on Tuesday that 14 equals the pH plus the POH so that you have those easy points for those. All right. Let's see. This isn't great because, yeah, it has all the answers. You can definitely go through that. So what's different with a weak acid or a weak base? It's only going to partially ionize in solution. So that means it's going to be in equilibrium with whatever its conjugate base is. So when it comes to finding the concentration of that, we're going to have to use that Ka value, or the acid dissociation constant, which, yeah, technically we could set up an ice table for that, but it's the Ka, the acid dissociation, is just going to be equal to the concentration of the products over the reactants, right? The same thing that we see over and over and over again when it comes to equilibrium. So acids are no different. You're going to do that. Essentially, the products are going to have the same in this case. So we're going to make that equal to x squared over that initial concentration. So when we're finding those concentrations, I guess I didn't take it a step further. We're going to make that equal to x squared over the initial concentration of the weak acid. From there, we can solve for x. X is going to be your H plus concentration. You can plug that back into pH. pH equals the negative log of H plus. All right. A little bit different with bases because we're using the base dissociation constant. It's just going to be the hydroxide concentration times the conjugate acid concentration over that initial concentration of base. So understanding how things change from acids to bases. I will say typically we see weak acids. On the exam, knock on wood, this year we'll see a lot of weak bases, but for the most part, we see mostly weak acids. All right, so all of these calculations are really important to understand and feel really comfortable with. All of this is on the formula sheet, which is super nice. So understanding that Ka and pKa, very similar to pH and H plus concentration, same types of equations. You also need to remember that the Ka times the Kb is equal to Kw. So being able to use that to then manipulate that to find Kb if you're given Ka, knowing that Kw is 1 times 10 to the negative 14th at standard conditions or standard temperature. All right. Yeah, you know what I'm going to plan on doing? Tomorrow night at 8:30, I am live with Chegg on their TikTok page. I'm just going to go through some acid-base calculations. So if you need some last-minute calculations, we'll go through that, just do some samples with those. So with this, we want to find Ka. K is going to be equal to the H plus concentration times that conjugate base over the initial concentration. We're given the Ka value. We then want to solve for X from that. And then you just solve for X. X is going to be equal to your H plus concentration. You plug that into the negative log of H plus and you get your pH. Yeah. Okay. All right. Okay. Can you go over assigning oxidation numbers? Yes, we will definitely go over that. All right. So these are all the basic equations that you need to know when it comes to acid-base chemistry. And then the ones in bold, again, you don't want to have to derive the log while you're taking the AP chemistry exam. So remembering that H plus is equal to 10 to the negative pH, it also, we can use that with POH, and just being able to rearrange that so you don't have to waste time on the math is really valuable. All right, so when it comes to titrations, here are the quick titration hacks. So let's go through those. So when it comes to strong acid, strong base titrations, this is the basic curve, what it's going to look like. If you notice, we don't have a half equivalence point. We only have the equivalence point. It's always at a pH of 7. That's because we don't have a buffer region. Because why? Buffers are only made with weak acids or weak bases and their conjugate pairs. You don't have a buffer system in a strong acid, strong base titration. All right. Versus a weak acid titration with a strong base or a weak base with a strong acid, you have two regions, right? Where we have the kind of the flat plateau that's known as the buffering region. That's any point up to the equivalence point, and that's where we're going to have the half equivalence point. Half equivalence point is a really important one to remember. It's just at half of the volume to the equivalence point, where half of the moles of acid have been neutralized, or half of the moles of base have been neutralized. And basically, at that point, the pH is equal to the pKa, and the pOH is equal to the pKb. You are probably going to see a question where you have to find either the pH or the pKa at that point. If you are looking at the half equivalence point, you don't have to use the Henderson-Hasselbalch equation because it essentially cancels out, right? Because when you have neutralized half of the moles of your weak acid, for instance, what does that mean? That means your moles of weak acid are equal to your moles of conjugate base. So essentially they cancel out, leaving you with a spot where pH is equal to the pKa. All right. So here's some more acid-base hacks. Just remembering these will be helpful. Also, I haven't talked about this yet. The higher the Ka or the lower the pKa, the stronger the acid. When it comes to choosing a buffer, you're looking for the conjugate acid-base pair, which never includes a strong acid or a strong base. Again, you cannot build a buffer with a strong acid or a strong base. When you're trying to choose an indicator for a titration, you're going to look at the pH range, and you want to find a pKa that is closest to that range. It might not match up. It might be that your equivalence point is at a pH of, I don't know, 6.2, and your best indicator ends at a range of 6. You're going to choose that one. You're going to choose the one that is closest. Okay, let's see. All right, this is a quick, easy multiple choice question. So I have a 25 ml sample of hydrofluoric acid, which we already said, weak acid, is titrated with sodium hydroxide, group 1 base. That is going to be a strong base. At the equivalence point of the titration, what would the pH of the solution be? So we know we have weak acid plus a strong base. Where is that equivalence point going to be? So think about that. Yeah. So what you want to remember is, okay, weak acid plus a strong base. That means the equivalence point is going to be slightly shifted towards that strong base. So it's going to be a pH of slightly above 7. So you can make predictions like that. If we had the opposite situation, weak base plus a strong acid, we'd expect a slightly acidic equivalence point, versus strong acid, strong base, it's going to be equal to 7. So I can't emphasize enough the importance of knowing what those 7 strong acids are, and then remembering the strong bases are groups 1 and 2 hydroxides. Because it immediately, when you're doing a titration or an acid-base problem, I want you looking at what you're given and identifying whether it is strong or weak, because that's going to make such a big difference. All right. This is another FRQ. So titrations tend to show up. This was an example of a sig fig question. So like I said earlier, there's 1 point on the entire exam designated for sig figs, typically a measurement or something to do with lab data. So looking at this burette, you need to remember that you're not just going to read this and say, okay, what is this volume? I can't see. This volume is, we're just going to make it up. 4.6. I'm not just going to read it based on the lines. You always need to remember to estimate 1 digit smaller than the smallest marking. That same thing goes for graduated cylinders. If you're making a volume measurement, you have to estimate 1 digit smaller than the smallest marking. So looking at this one saying, okay, 29.54 minus 3.36. Did you get those exact same measurements when you looked at it? Maybe not. But what matters is remembering to estimate 1 digit past. So there's going to be a range of accepted answers with this. Don't spend 5 minutes trying to decide whether you want to estimate to 5.4 or 5.6. It does not matter. You just have to show the estimated digit. So just be careful with that. This is just an example of another simple problem, right? Showing just the concentrations. These are the types of problems that you will see the most of. You might see, right, the weak acid, strong base calculation where you're looking at the pH at different points of that titration. But also know that like knowing these types of calculations is still really valuable. Okay, Henderson-Hasselbalch equation. So this is what you're going to use to calculate the pH at any point in that buffer zone. So if we're doing a weak plus strong titration, the buffer region again is any point leading up to the equivalence point where we know the pH is equal to the pA plus the log of the conjugate base over the conjugate acid. So with this, a lot of times you're going to end up with moles, and that's fine. So let's say we're using a BCA table. You found the before, the change, and the after, and you end up with moles of conjugate base over moles of your weak acid. That's totally okay. They are in the same solution. So if you took the time to change that to concentration, you would get the same answer. Okay. So it can be concentration or it can be moles. Don't stress out about that. And again, remember at the half equivalence point where we have neutralized half of our moles of acid or moles of base, pH is equal to the pKa. All right. So buffers. I already mentioned this earlier, but basically a buffer is going to be a weak acid and its conjugate base, which resists changes to a pH up to a certain point or its buffer capacity. And that's all going to be dependent on the concentration of the conjugate acid and its the concentration of the acid in its conjugate base or the base in its conjugate acid. So 1-to-1 ratio is the best. It's going to have the highest capacity, and the higher the concentration, the higher the buffer capacity. We don't actually have to do any calculations in AP Chem now with buffer capacity or anything like that, which is really nice. But understanding the basics of it is helpful. And then this, I would argue, is the hardest part on the entire exam, which is why I've been trying to release a lot of helpful things to help you out with this. Yeah, so you should have access to this again in the notes. I've shared this multiple times. This is going to show you how all of those pH calculations are going to change based on where you are in a titration. So when you have a titration problem, you're going to first identify whether you're working with a strong or a weak acid or base. You're going to identify those first. Then you're going to think, okay, at what point am I in this titration? If you don't know the volume to the equivalence point, you're going to calculate that. Okay, you're going to find the moles of whatever you're given. You're going to use the concentration of the other subject, the titrant, and you're going to find the volume needed to reach the equivalence point. Because then you can say, okay, if the equivalence point is at 15 milliliters, but I've added 7.5 milliliters, oh, wait, I'm at the half equivalence point where pH is equal to the pKa. I was given the Ka value. I'm going to find the pKa, and then I'm good. So you have to think through it. So you're going to identify the strength of your acid or base. Then you're going to identify where we are in that titration. And then you're going to rock it, right? And you're going to be totally fine. Let's just hope that we don't have to calculate the pH at the equivalence point because it just gets a little dicey there. But my goal is to release one more video tomorrow, just talking you through that. And again, I'll be live tomorrow night with Chegg, and we can go through that too. All right. I have not been reading the chat. I'm so sorry. Yeah. All right. Let's keep going. All right. So last unit. So thermo and electrochem. I think a lot of students get overwhelmed by this, right? Because there's a lot of this that maybe you just got to it last week. Maybe you haven't gotten to it yet, but there are certain things that really are not difficult. Okay. So when it comes to this, understanding what's happening and understanding that, oh wait, we are looking at some really simple ideas and I can do this. I can figure this out. So when it comes to entropy, understanding that an increase in entropy, right? The bad definition is going to be the measure of disorder of a system. Really, we're talking about how much that energy, matter has spread out. So looking at these in this multiple choice question, right? We're looking at we're changing state. So if we think about a solid just barely moving versus a gas moving like crazy, right? What's happening? If we are dissolving something in this case, we're going from the solid to the aqueous ions. That's going to be an increase in entropy. This is not as fun that you can see all the answers. Can't even use my PowerPoint tonight. But basically, we're looking at an increase in the number of molecules. We're looking at a change in the state. Are we going from the solid to the gas phase? That would be an increase in entropy. That is positive entropy. That is favorable. All right, calculations, same as what you learned in Thermochem, always products minus reactants. Gibbs free energy, same thing. And then with Gibbs free energy, knowing delta G equals delta H minus T delta S. This is where we started this session, right? Understanding what is considered thermodynamically favorable, remembering that delta G always has to be negative. What conditions do you need to make sure that delta G is negative? All right, and then also understanding that even if delta G is negative, doesn't always mean that it's going to proceed to equilibrium. So we can also have it might just have a really high activation energy, and this is known as kinetic control. So understanding that definition. So even if everything looks like it should be favored, it might just be happening so slowly, it's hard to tell, in which case we're going to add a catalyst to speed that process up. All right. Yeah, that's all. Coupled reactions. Understand that with coupled reactions, you just want to find the shared intermediate. You want to make sure that your Gibbs free energies, when you add those together, you have a negative value, right? All connects back in. Um, yeah. All right. Let's end with electrochem. When it comes to electrochem, basically, we're just going to be looking at being able to identify the type of cell that we're looking at, right? Are we looking at a favored process, in which case this is going to be a galvanic or a voltaic cell? We're going to see that salt bridge. We need that salt bridge to balance the charges. Or are we looking at an electrolytic cell where we have an unfavorable reaction that we are kind of forcing with electricity? So what's going to always be true? Oxidation is going to happen at the anode. Reduction is going to happen at the cathode. Electrons are going to flow away from the anode and come to the cathode. The cat is going to get fat. The cathode is going to accumulate mass as the cell operates. And once equilibrium is reached, guess what? Your voltage is zero. You have a dead battery. We don't want to reach equilibrium in these electrochemical cells. This is one case where you don't want to reach equilibrium because then you no longer have the transfer of electrons and your cell is no longer operating. And then we're going to use that salt bridge to balance the charge. The positively charged cations are going to go to the cathode, negatively charged anions are going to go to the anode. All right, and these are all the mnemonics that I just dropped as I was going through that. Again, electrochem is counterintuitive. Make sure you have these down, even if you want to write these down on your scratch paper so you can look down and be like, oh, wait, yeah, oxidation is loss. That just lost electrons. That is oxidation. That is happening at the anode because I remembered an ox. It seems so silly, but when you are stressed on Tuesday and you're trying to fly through, it makes a big difference to just have those basics down. All right, so we talked about that. This was an example of an FRQ that kind of threw everybody. I can't remember this last year or the year before that, but we had this image of a battery, and everyone's like, oh, where did that come from? Don't worry about that. All you needed to do in this problem is write the balanced net ionic equation for the reaction that has the greatest thermodynamic favorability. You remember, oh, wait, I need a positive cell potential. How can I add these reactions together to get the most positive option? And then looking at this chart, remembering the reduction half reaction, anytime you have those reduction potentials, they're given as reduction potentials only. So that means that any oxidation reaction is either going to be really negative or only slightly positive. So you're going to flip the sign of that and add that to your reduction. All right, the other equation, this is the big equation that is not on the equation sheet. The cell potential is equal to the cell potential at the cathode minus the anode. The bigger the difference, the higher, the more positive that cell potential, the more favorable the reaction. Some teachers will teach you to flip the sign at the anode and then add them together. That's great too. I think it's easiest just to keep the reaction like this. So you don't have to worry about that. You're pulling those values directly from your table of reduction reduction potentials and just plugging that in. All right, the other equation you need to know is delta G equals negative NFE. Remembering that N is the moles of electrons involved in that redox reaction. F is Faraday's constant, and then E is that cell potential. These are really easy points. You're just multiplying things together, making sure that you get the right number for the moles of electrons. Again, you need that from the balanced reaction. Okay, this was just an example FRQ. You can definitely check this out. It seems really simple, but College Board seems to like asking for the missing salt bridge or the missing battery in an electrolytic cell. It can be that simple. Okay, let's see. Yeah. So that's just practice with using those two equations I just talked about. And I know I've posted quite a few videos on that as well, so you have that. All right, non-standard conditions. This is the harder part of Unit 9. So understanding that at standard conditions are 1 molar solutions or 1 atmospheres in pressure. We don't see that too often. Typically, we're looking at solutions and a temperature of 298 Kelvin. So at that case, Q is equal to 1. And the cell potential is going to be dependent on the concentration and pressures of the reactants and products. So, what is a non standard condition? It's just any change in that. It can be just a slight change in temperature, and that counts. We can't use Le Chatelier's because we're not talking about equilibrium, right? We don't want our electrochemical cell to be at equilibrium. So, we can't think about it in that way. So, instead, you're going to use the Nernst equation. So the Nernst equation is this one. It is on your formula sheet. You will never have to give a quantitative value with this, but what we can do is we can think about Q, plug it into the Nernst equation, and then see how our cell potential changes. So if the concentration of product increases, Q is going to increase, and that means that our cell potential is going to decrease when we subtract it from the initial cell potential. So understanding how to then make a difference in that. All right. And this just shows all of those non-standard equations, so conditions. So if you'd rather just memorize this, you have that, but you need to be able to justify it with the Nernst equation. The other big thing is Faraday's law and electrolysis. I think the tricky thing with this is understanding kind of how these equations can change based on what you're looking for. So you're going to be using the Faraday's constant, which is 96,484 485 coulombs per mole of electron. And you're basically just going to be doing conversions until you get to the quantity that you need. So in this case, we're looking at mass. This video would show it, but I can't use any of my slides. Oof, what a mess. I'm so sorry. Thank you all for being here. I hope it's been at least helpful tonight. All right, so with this, we're looking for a mass of nickel. You can watch that. And we're basically just going to, let's see, maybe I can get to play. I was trying to find a good way to show a whiteboard. All right, there we go. Like I said, tomorrow night, I'm actually going to be live at my whiteboard at the same time, so we can actually go through. And I'm just going to plan on doing like titration, calculations, and electrochem. All right, so with Faraday's law, there's no way you're going to be able to see this. But definitely check out the links so you have it. You're going to be making sure that all of your units match your constants. You're going to be careful with it. And the really nice thing about your formula sheet now is that you have a lot of the conversions and units built into it. So if you can't remember what a coulomb is equal to or what a volt is equal to, you can then look at those conversions and use that. Use the units to your advantage, okay? And I'll plan on doing this tomorrow night too. I feel so badly that like nothing worked out the way I intended it to tonight. All right. So Faraday's law, the reason this gets tricky is you can't just use it just to find the mass. You can find the number of electrons transferred, the time the cell is operating, but it's just a matter of making sure that you're using Faraday's constant, the coulombs per moles of electrons, and you're setting those up to convert between whatever you're given to whatever you need in the end. All right. Things to know. These are the equations not on the formula sheet. Again, I'd argue these are the big ones. And then understanding thermodynamic favorability. Just add that to the list of things to memorize. Hopefully there's not like I do have a list of things to memorize. Let me go through that again. All right, things to memorize for the AP chemistry exam. Polyatomic ions, rate law graphs, conditions for thermodynamic favorability, the equations not on the formula sheet, like the E dot cell equals E dot cathode minus E dot anode, solubility rules, as in memorize what's always soluble. So group 1 ions, acetates, nitrates, and ammonium, always soluble. Knowing that is really helpful. What else did I say? I think I said one other thing, but I think also you can find just like a doc of all the things to memorize just to make your life easier. All right. I've been talking for way too long, and I feel so badly that things did not work out the way I intended them to. So I will keep working on this and building more. But at this point tonight, I don't want to hear that you stayed up until 3 a.m. I want you to sleep. You've been putting in so much work up to this point, whether you feel like it or not. You've been learning some good chemistry. And I will tell you, looking at the tests from the last couple of years, the practice problems you've been doing in class are going to be more tricky than the ones that you are going to see. So I want you to pack your bag tomorrow night. You have an early exam. You have an 8 o'clock exam here on the East Coast. That's an early morning. So I want you to pack your bag on Monday night, put your calculator in there, put a snack in there, and don't forget to eat before you go. It is a long test. Get early, laugh, cry with everybody else, and get ready. And then the joke is mention Coulombic attraction as much as possible. So I will end by saying a score does not define you or your experiences in AP Chem. You're going to walk away a stronger student, a stronger math student, and just more ready for whatever's coming next. So be proud of all that you've learned and all the work you've put in, and know that I'm cheering you on from afar. This time in 48 hours, you can be chilling a little bit, unless you have like 3 other million AP exams, which I'm sure you do. So hang in there. All right, let me see. Anything else in the chat? Yeah, definitely bring pencils. You guys, no, you guys are gonna be fine. I know, the full Faraday's law. You know what I'm gonna do is I'm gonna update these slides and link actual examples. This did not work out the way I intended to tonight. It's such a bummer. Yeah, and you know what? AP Chem, I like to say it's an experience. It is an experience. You walk away from this class, you're more ready for just about everything. When I was a grad student at UVA, I was teaching a Gen Chem lab for pre-meds. And do you know what the class was that was the weed out class for pre-meds? Like first semester, freshman year, it was Gen Chem. Who was leaving their dream of being a doctor, being in medicine at all? It was all the students who hadn't taken AP Chem. So if you are taking AP Chem because you want to make sure that you are ready for Gen Chem or for a career in STEM or healthcare or anything else, like it's worth it. It's worth it no matter what score you get. And I will say the exam scores are trending to be higher than they used to be too, which, that's nice to hear too. Yeah. Mechanical pencils. Yeah, but you don't wanna use anything that is like an erasable pen or anything like that, because think about, like, they're taking those FRQ booklets, they're gonna be traveling. If they are in a hot truck, heat erasable pens, things like that are gonna disappear. So erasable pens, things like that. So you wanna just make sure you're not doing anything silly like that. Yeah, where's the Chegg live stream? So I actually host a weekly office hour with Chegg on their TikTok page. So if you go to Chegg's TikTok page tomorrow night at 8:30, I spend an hour just answering random questions. We'll have one stream tomorrow night and then one more on the 12th for the semester, because most college students are done. Sorry to all my high school kiddos. I know you still have a few more weeks, but once you get through AP exam season, it feels like you are done, right? I'm sure a lot of you have been. Spring is just so busy too. Yeah, what appears most on the test? So it's Unit 3. So Unit 3 is up to 22% of the exam. Unit 3 covers IMF, gases, properties of solids and liquids, all of that. That's Unit 3. The second highest weight is going to be acid-base chemistry. Yeah, so tomorrow the plan is I do a live stream at my whiteboard. So that's literally all I do. It's just practice problems. No, it's not. It's not on YouTube. It's only streamed on TikTok now. So it's gonna be streamed on Chegg's TikTok. Yeah. So, and I wanna encourage you all to do something to celebrate being done with the AP exam. Go get ice cream, celebrate all those ice tables and things like that. Like, you should celebrate being through this exam. No, you shouldn't have to do quantum numbers. Nope. Delta H and Q. Yeah. So delta H is the enthalpy, so that's gonna be the difference in energy between the products and the reactants, versus Q is just the quantity of heat. Yeah. Let's see. Do they check what's on in my calculator? No, they do not. They do not check your calculator. You do not have to clear your calculator. Oh, I forgot to talk about assigning oxidation numbers. Yeah. So when it comes to assigning oxidation numbers, oxidation is just a fancy way to describe the charge, right? Sure, I can shout out your sixth period AP class and Mr. S. What's up, sixth period? But yeah, so when it comes to oxidation numbers, it's just assigning charges. So if you are looking at the molecule, right, you want to start with the ones that are kind of set, right? So if you have a molecule and it has oxygen in it, oxygen is always -2. So use the negative portion of the formula to work backwards to figure out the positive portion, kind of work with what you know, and then go from there. How about I'm going to add that to my list for tomorrow's Chegg. So just assigning ox numbers, just to give you some examples. It's just one of those situations. So you can start looking up oxidation numbers and formulas, find videos out there or just descriptions that kind of show you. And then the more things that you expose yourself to, the easier it's going to feel. Yeah. Slide 205. Yeah. Okay. Yeah. All right. Let me see 205. Okay. Electrochemical cells. Yeah, all right, so this was an FRQ from, I think, last year. So, what this was supposed to say, you can't see any of my, like, um, animations or anything like that, but basically, this was an electrochemical cell that we were given. This is an electrolytic cell. It's a battery essentially. And everyone saw this diagram with the paste and all of that. And you're like, what is going on? And basically, you have to block that out. You have to look at it and you just say, okay, I'm not going to worry about this diagram that makes no sense to me. I'm not going to worry about this term that I've never seen. I'm going to jump down to part I, where it says, based on the half reactions given in the table, write the balanced net ionic reaction equation for the reaction that has the greatest thermodynamic favorability. So if I'm looking for the greatest thermodynamic favorability, I'm looking for the most positive cell potential. So when I think about the cell potential, right, it's going to be the cell potential at the cathode minus the cell potential at the anode. So the cathode is the red cat, right, is where the reduction happens. So looking at this, we're looking at the most positive value. So this one here, this last reaction with the manganese dioxide, manganese oxide, that is going to be my reduction. So that's where I'm going to start. So I'm going to have 0.15. And then my goal is to find the most positive cell potential total. So if I then subtract the oxidation reaction, if I subtract a negative, I'm adding that. So I'm going to pick this reaction as my oxidation. So basically with this one, I wanted to look at these and say, okay, how can I make the most positive cell potential happen? And that's kind of how I'd walk over that. Yeah. Okay. Sorry, let me go back through. Yeah, column chromatography and okay, here. Sorry, let me go back. Yeah, there are a good amount of videos out there for molecular geometry and whatnot. Yeah, and they do not check your calculators. That is absolutely a sure thing. I was reading the calculator guidelines, I think yesterday, just to make sure, because someone was like, well, we have Desmos. Like, yeah, you have Desmos, but you also can bring your calculator. And it literally says on College Board site, like, do not have to clear the memory of the calculators. Okay. Yeah, how can I teach myself all of Unit 9? So I actually have, like, a complete Unit 9 video, that's on my YouTube. I also have a problem set linked with answers and things like that. Watch some videos, see those practice problems being worked through. Jeremy Krug is awesome. He's done everything that I wish I had time to do. He's posted so many incredible videos that are nice and short and sweet to the point. Definitely check those out. And focus on, like, the big ideas, being able to calculate the cell potential, identify the cathode versus the anode. Those are some of the big ideas in Unit 9. Okay, so column versus paper chromatography. We have all kinds of different types of chromatography. We have gas chromatography, liquid chromatography. What you need to know is the basis of it, right? It's a separation method. So understanding that we are using column chromatography to separate mixtures, right? Based on either the polarity to the solvent or the solute, just understanding that it's just a separation method is pretty much all you need. Let's see. Lab setup. Yeah, okay. So when it comes to lab setup problems and things like that, it's so the hardest part is, again, being able to block out all of the extraneous information. I'd say if you have a lab setup problem, you're going to have a big chunk of data that you're given. There's going to be something that's empty where you're going to have to just separate. You're just going to have to subtract. And understanding that, okay, this is all of this problem. Let's jump down to what the question's asking. Read what the question's asking, then go back in to the actual lab description and figure out what you need to know for that. I actually just made a quizzes that was based all on lab-based FRQs. I'm going to add a link to that in the video notes so you have it. But that's just like all of the most recent lab-based FRQs so you can see them. Quizzes isn't the easiest way to do that, to work through them, but it just so you get more exposure to those types of questions. I'd say just like not freaking out about the amount of information that's contained in those and just focusing on what the question's asking for, because you are just doing simple analysis most of the times. You need to find the mass. You're then taking the mass, you're converting that into moles, and then going from there. So just be really careful with that. And again, when you are actually doing a volume measurement, anything like that, remembering to estimate one digit past the smallest marking. Yeah. Yes. So, do we have to describe and write procedures? That's a really good question. Solutions tend to come up. So, how do we make a solution? You take the solid, the big things you need to know. You take the solid, you put it in a volumetric flask. I definitely have volumetric flask hanging out around here. I don't think I have one within reach. Oh, I do. Look at that. I'm such a nerd. This is a volumetric flask. So you're going to take your solid, you put it in the dry volumetric flask. All volumetric flasks are going to have a line right on the neck of the flask. And guess what? There's only one volume measurement. So this can only be used to make a 50 milliliter solution. So with that, you're going to take your solid, you're going to put it in there. You're going to fill this with distilled water to a certain point. You're going to then get the solid to dissolve before filling it up to the final volume where you get exactly to that single mark on the neck. So that is the process for that. So big things you need to know, you're using distilled water. You're putting your solid solute in first. You're using a volumetric flask that matches the volume that you needed. And then you are mixing it until that solute all dissolves. So that's the big lab procedure that we have seen last couple of years. Of course, now that I've said that, that's not what we're going to see, right? Yeah. And that's so true. If you do well in everything else and still fail the lab ones, you could absolutely still get a 5. So keep in mind, you need like a 70 something to get a 5 on the AP exam. You know, 70% is you can still miss a good amount of questions, still have no idea what's going on in some of them and still do well. So know that when you walk in on Tuesday and you look at those FRQs and you're like, whoa, I am so cooked. I have no idea how to do this first one. Don't stress. Okay. Immediately go to one that you feel confident with. Do that, knock it out, go through that. Always answer everything that you can. Again, remember, error carries forward. So if you don't know how to do parts A through C, give a value, use it, run with it, and still rock parts D through F. Yeah. All right. I think I feel like I'm sick of hearing myself talk. I don't know about you guys. So I'm probably going to get off. Yeah, thermodynamic favorability. So when it comes to cell potential, you want a positive cell potential value. Cell potential is just going to be the difference between the cathode and the anode. You want the most positive value. That's going to indicate a favorable reaction. So that's what you're looking for. Yeah, and a lot of times that's true. Like in the FRQs, it's very rare that you have to write out the whole procedure. It's more that you're filling in spots, which sometimes can be tricky if you don't want to phrase it in the same way. Um, Yeah, which units show up on the FRQ the most? So unit 3 just shows up on the test the most. Units 3 and 8 have the highest weight. But I will say, like, you still see stoichiometry in a lot of the questions. Last year's test, I feel like a lot of honors chem students could have done well with it because we had stoich in so many places. So if you're feeling good about stoichiometry, like, don't stress. That's okay. Like, that's great. It's a good starting point. Yeah. Yeah. Yeah, so everyone's gonna have a different approach, right? But you can start with the short free response questions and then jump back into the long ones. You don't get penalized, right, for the order of the questions that you complete. So it is totally okay to preview the exam and just kind of jump around. Again, keeping in mind you're not going to be penalized for wrong answers. So you do want to make sure you save enough time and you try to get as much written down as possible. Yes, and that's correct. So unit 3 is 18 to 22% of the exam. Let's see. If a molecule is polar, yes, it experiences dipole-dipole interactions. Yep. You don't need to know the physical shape of S versus P versus D. Nope. No, yeah. Yeah. So error carries forward is it's just this idea that if you made a mistake in the initial part of an FRQ, you're not going to be penalized for it later. So if you do all of the rest of the calculations correct, but you messed up your mole conversion in the initial step, like we're not gonna penalize you for that. You'll still get full credit for the other calculations. Yeah. Um, 3.11. Yeah. Let's see. I'll do 311, and then I've been on for 2 hours, so I'm gonna hop off here in a second. Alright, let's see. 3.11. I think I had slides for it. Let's see. Okay. Yeah, spectroscopy. So when it comes to spectroscopy, understanding how to use these equations, and understanding that. So EMR, just understanding that wavelength and energy are going to be inversely related. But again, just making sure that you're converting your wavelength from nanometers to meters to match. It's just like any other equation. If you're doing Beer's law, I think that's in 3.12. Yeah. So 3.12 is Beer's law, right? Understanding that you are either looking at a graph and just finding the concentration, or you're solving for a missing variable. You're just going to always use the units to your advantage. You probably haven't spent as much time with these calculations, but if you see this, don't be intimidated by it. You know how to rearrange the equation. You know how to use your units to then find the answer that you need. Yeah. Yep. All right. So with that, I'm going to say good luck. I'm going to keep adding to these and updating these, since this was such a fail as far as like sharing this with you all. I'm so sorry. Um and yeah, you are going to be fine. Okay? So take care of yourself. Be ready to rock it. Pack everything on Monday night and be ready for that 8 a.m. exam. And I can't wait to hear how it goes. So, yeah. All right. Have a good night, everyone. Hang in there.